So today I will try my best to cover 3 lectures. I will not cover the lecture 4, which is linear regression, mainly because pretty much it will not be used in your next lab and your homework this coming. Yes, but I will maybe provide that as additional lecture, maybe next Monday. Yeah. Okay. So let's start from lecture 1. So in this lecture, we will talk about like a simple concept of what is statistical modeling, what is statistical inferencing, and what is statistical learning. And yes, the bias variance curves that we kind of seen roughly previously about overfitting, underfitting. I think these terms are very important to understand because they are very fundamental in statistical learning or machine learning. Pretty much, I would like you to think about this course as the time where you study about machine learning. I'll put it this way because most of the tools that we will be learning are about machine learning techniques. Okay. So yes, these are the prerequisites of this course. So there are statistics, mathematics, optimization, and Python coding. But I would highlight the optimization. We will use quite a lot. But it's more about that you see the optimization problems and understand the underlying meaning. Probably I wouldn't ask about derivation or anything like that, but just to know what's the meaning of that. And about mathematics, we will use lots of linear algebra, and I think the statistical techniques or probabilities, something like if I ask you what is the expectation of this random variable and how to compute covariance, something like that, you have to kind of have in mind what that means. Or maybe joint distribution, something like that. It will be quite useful for this course because lots of the derivation and how they come up with this idea or solution, they are all based on statistics, most of them. Okay. And what's the objective of this course? Mostly, okay, as you can see here, I would like you to know how to, let's say, extract the properties or use the right measurements to visualize the data. Pretty much, how can you extract the properties of your data? And visualization is one of those things that you have to do. Second, we would like that you be able to choose a suitable tool for solving a given problem. What is a suitable solution if you are given this type of data, something like that. And maybe apply those two to solve some real-world problems. And finally, analyze the problems in the tool that you choose. And this is something that could be difficult, but I think in this course, it should give you some clear idea of what tools you are using and what are the drawbacks between them. And yes, again, the coding lab will take about 25%. If you attend most of the classes of the laboratories, you should get this as a full score. Homework is another 25%. For your exam is 50%, 25 for midterm and 25 for final. Yeah. So it's not, I think it's not too bad. I mean, if you attend every coding lab, 25% is given. And if you do most of the homework that you understand what you're doing, it's 25%. But yes, some of the homework will be more challenging than others. Some of them may require some time for you to run. So it's best to, I mean, on this Wednesday, after you finish your quiz, I recommend you to try your homework right away because that is when I will know whether or not you have problem running this algorithm. Most of the time I run these codes in my computer, but my computer has, let's say, 42 gigabyte RAM, which is like 4 times of the generative 16 gigabit RAM, which means that I will run it faster and I may not feel that it's an obstacle for me, but for you it may be. So that is something to help me as well, whether or not I need to extend your time or should I keep it as it is. And by the way, given the fact that we're talking about the homework, for each homework at the moment, I schedule it to be like, let's say the time for your homework is to finish it before the next laboratory. So for your first homework, which is going to be on this Wednesday, you will have to finish it before the next lab, which is, I think, another 2 weeks away. Let's just look at them. Sorry?
Is it first Monday of February?
I am not sure, but let's look at them.
First Monday of February.
Yeah, it's the first Monday of February. So, but if this is like the amount of weeks that you have, please don't worry, it will not be a lot. Okay, most of them aren't that extensive as it used to be compared to the previous year that I've run this course. I used to make like an entire homework for students to create their own deep learning. So I know that that takes too much time right now. So this one will be more like you fill up the gap. Or maybe from the Python code that you have, can you analyze the result? Or maybe extend something so that you can run. But usually it's like a full package is where you can run already. Yes, that's pretty much it. Please don't worry. Okay. And next thing, okay, let's start our content. So what is making inference? I think if you've used maybe machine learning or deep learning before, you probably heard of this term quite often. It is inference, strictly speaking, it is the time where you give an input to your model and you expect that model to provide you an output. That's it. That is an inference. And the reason that we have to have the name for it is because in machine learning world or statistical learning, there are the learning phase. And the inference phase and learning phase should be something that you can well separate them. Because first, very likely you are going to use the same model, but you are using that model for a different purpose. And second, you will be applying different types of data. There are testing data for your testing phase. There are training data for your learning phase. And there are validation data when you want to do the validating. And we will talk about how each of them works. Okay, we just start a little bit so that you can sit up. Okay. Yep. All right. So in this example, the kind of inference that I'm making is what we call discriminative. Or discriminative task. Let's call it discriminative task because we are making this inference for a discriminative task. Okay, I don't know why it gives me these red things. Okay, discriminative. It's actually TIVE. I don't know why it's giving me this recommendation. Discriminative. Inference for discriminative task or other task are something very similar. You are receiving input and you're providing an output. But the reason for me to call this one discriminative is because the kind of output that you want is something that, let's say, is maybe the space of your output is something that is limited. In this case, is the classes of the animal in the picture. Let's say if you fed an input picture of a hamster and your model can predict that that's a hamster, and perhaps there are other types of animal, but these types of animal are within a finite set. then we call it a discriminative task. So the gist is about the output space. Is limited. Another task that we also call discriminative in this course is a regression task. Regressions is discriminative even though the output may not be class. It's because usually we want the model to provide like a value within a range, let's say 0 to 1. So it's still kind of limited within like a range of value. Or if you were to use this model to, let's say, predict the price of the house, usually the price of the house will lie, let's say, within, maybe in Thai baht, it's like around 100,000 to millions. It's like a price of a house. It probably won't be something like 10 baht. Yes, so there are limitations into what is the what is the value of your output will be. And usually the size of the dimension of your output is going to be small. Let's say when your output is a hamster, maybe a hamster, a pony, or a kitten, or a parrot, it usually can be mapped to a single digit. Let's say if you say that the class of a cat is 0, a class of a dog is 1, you can provide a numerical representation that is finite as well. So it can be like a discrete number. This may be slightly different for a regression task, where you have like a price of a house. It could be like more like a continuous price, but usually the range is limited. It's still considered as discriminative because you are discriminating what the output could be. You are discriminating, let's say, given an input, you are discriminating them to what the output could be. So this is like a common properties of the discriminative model. Okay, let's go to the next one. This one is also making an inference, but is more like a generative. Actually, it's my example of generative model. Generative model is different from discriminative for a very important reason, that it can provide you whatever outputs. Let's say if you use ChatGPT, you probably know it as generative model or maybe generative AI. And yes, we are talking about those stuff. In generative model, especially text to image generation, your output space for your image can be anything. Let's say someone may not be as humble as my example. In this example, what I was trying to say that please generate, or maybe give me an output of a pet animal. Let's say for my first statement, it could give me various results, and they are correct because they are pets. But if I add more conditions such as with whisker and fur, then yeah, maybe my output space will be more limited. But please keep in mind that there are more types of animal than this showing that are animals with whiskers and fur. But the good things about generative model is that the more text you add, usually it gives you the more constraint as to what your output could be. However, even though you can add this constraint in generative AI these days, you can add a very weird constraint like, give me a picture of a cat with long ear and that cat is running on Mars with the astronaut hat and it was running on a rainbow. It's super weird and specific, but it's something that generative model has to do. So it can give you an extreme output out of your common data set that you've never seen before. So the gist of generative model is that you are asking the model to generate something that is unseen, that is possibly lying within a very large output space. So that is like a common nature of a generative model. But whether or not it is a generative or discriminative, both of them has the same common function that I would say is a inference function. That is, when it's given an input, it has to provide an output. And usually when we talk about inference, we will talk about the inference that we use when we are deploying the model. Let's say when you want your user to use it, or you want to test the performance, that is when you would do inference. So maybe let's look at a bit about the pipeline of the whole entire thing. So yes, when you first have your data, you have to do something about it to make sure that it will work in your pipeline. Sometimes you have to do the cleaning. Sometimes you have to do the feature selections. Sometimes you have to, like splitting the data for training, testing, and validation. And we will talk why there must be validation. I think lots of people tend to confuse validation with testing because it's pretty much running model in the inference mode, but it's for a different purpose. Okay, and after you splitting your data, preprocessing your data, the next thing to do is to do with your model, where your model will be probably first, if you want to tune your model, you probably have to train them. But after training them, you may have to do something like validation and testing. And testing is pretty much evaluate your model performance. But I would like to kind of tell you at this moment that sometimes some of our scores will be run while you are doing the training. And I will let you know when that happens. But most of the time, when we talk about performance, it will be on testing. And validation is for something else, but I will tell you right away after these slides. And yes, another thing that we have to learn in this course is how we're going to evaluate your model, the model evaluation or performance evaluations. And probably you are familiar with these two types of evaluation, MSE, mean square error, and next one is peak signal to noise ratio. Peak signal to noise ratio is usually like a kind of evaluation matrix when you evaluate the quality of the image, the picture. Usually this one will be used with your generative task because it's kind of quantifying the quality of your output. Meanwhile, mean square error can be used for both discriminative and generative tasks. It depends on what you're doing. But yeah, this is more like what people commonly do. Generally. Any question? Okay. Okay. And yes, aside from this pipeline, there are various types of model. So today I will do my best to cover all of them. But maybe let's talk a bit about our setting, and then we will go over the model, but we talk about setting first, so we know what are the training, validation, and testing stuff why they need to be there, and what are they used for. Okay. In our course, Statistical Learning, I will use the following notation as well as to set up our setting. So firstly, most of our model in this course are discriminative model. Okay. When I say it's a discriminative model, as I mentioned before, yes, the output should be within a range. It could be classes, it could be numerical value, like within a range, something like that. So we are not doing generative model. Generative model probably require like another course for that. Okay. Oh, I know now, I forget the S. Discriminative task. But within this discriminative task, some of them may have, or maybe some of them may be using something that we call like a generative combination. But usually they do that to learn the model parameter. And then when you use that model, you will still run it in discriminative way. That is, you will still use that model to do discriminative task, but its model parameters may be learned discriminatively or generatively, it depends. But we will talk about that in detail later. This is more like to give you an overview, like a prep for what can happen. Yep. So yes, in statistical learning, because we are talking about discriminative task, usually our input, sometimes we will refer to it as independent variable. This input will be called input features in our lecture. But just letting you know, some textbook may be calling this input as predictors. But I don't want to use that name because it's confusing. But just letting you know, sometimes it is actually called that way. But let's call it input features or just an input or inputs, depends on how big that input is. Okay. The next thing is the output, which is sometimes referred to dependent variables. Dependent variables mean it's a variables that depend on the value of the independent variable. So let's say you may sometimes write that as a function, that is y hat is equal to function of x. So yes, that when we put it that way, this is dependent, this is independent, because x can be anything that will give you the value of y hat. Okay. And sometimes we may call this output as predictions. Yes, that's why I don't want to call the first one predictors, because it can be very confusing. Let's just say we call it prediction results, predicting labels, predicting values, or maybe predicting target. When there's the word predicting, usually this means that this is like a predicting result of your model. Okay. But yes, in the textbook that call input X predictor, it calls output Y hat response. So this is like a pair if you found these terms in the textbook. But just letting you know that we probably wouldn't call it this course because we have too much to care about. Okay. And last thing that we need in our learning system is what we call reference. Reference is needed for two reasons. The first reason is that we use it in training the model or learning the model parameters. That is your first objective. The second benefit of it is to use it for evaluation or validation. So that's why you need reference. Okay. Nevertheless, there are two types of reference that I would like to ask you to be careful about it, because let's say most of our evaluation are going to be based on the noisy reference. And usually noisy reference is going to be referred to as the measurements. When people say measurements, usually it means that there are noise associated with the sensors that is interference your observation. For example, if you has any of you use sensors in collecting data? What is a sensor?
I use current sensor.
What?
Current sensor. Current sensor.
Current sensor.
Yeah.
Yeah, possible. The current sensor could be interfered by some kind of noises. Maybe that one came from a resistor in your system or capacitor, we don't know. But yes, those stuff could create noise. And usually noise in these sensors, or what we call measurement noise, cannot be removed. At least in this course, most of our tools or models are not designed to handle these types of noise. So we will call it like irremovable noise. Or maybe we say that these types of reference have something that is called like an irremovable noise. Okay, but also there are, well, the best possible version of it, that is the noiseless reference. And usually when we say it's a noiseless reference, sometimes people will use other term, that is the ground truth. Ground truth is commonly used, especially in the field of computer science. Usually, probably because in most of those applications, they have a data set that is already cleaned, and some of them are clear in what they are representing. Therefore, they can call their reference ground truth. That means absolutely no noise. Okay. So yes, in most cases, we evaluate with the noisy reference and learn with the noisy reference. But also, as we will see in later on, we will try to map our performance back to the noiseless reference as well by decomposing the noise term in the noisy reference or our measurements. Sometimes we try to separate the noise out of the measurements so that we can recognize what is the performance versus the ground truth or the noiseless one. But usually when we do the training, there is no way to avoid it. So yes, data cleaning is very important when we do machine learning, because we have to make sure that our reference could be a good representative and it will not deviate too much from the reality, something like that. Yes. Okay. Finally, this is like a recap of if we have y hat is the output of our model, and usually we prefer that the y hat will be capturing, let's say, the ground truth or the clear noiseless reference plus the noise, which is actually the noisy reference. So this is like what we can evaluate. It's probably pretty much at the end is with respect to our measurements. But yes, we will do our best to separate our noiseless version out of it. Yes. Okay. Shall we move on? So there are 3 steps in, let's say, creating a model and using it. The first step is the training. And pretty much in this step, we will do our best to find either the model or the model parameters. Or let's say we are learning these 2 sets of unknowns. That's the training steps. And this training step will correspond to training data. So pretty much when we have like, let's say, a bucket of data, right? We have to separate them first for training. But then also, I would like to jump to the last one, the testing. And the reason that I jump down here is because if in your training, you train a model and that's it, you don't want to consider any other impact from your setting, you want to just use that model, you can just evaluate it with the testing step. And in this testing step, you'll be using what we call testing data for your evaluation. But of course, in both training data and testing data, you need to have input features and your measurements reference, or it could be ground truth. It depends on your task. What I haven't described yet is the validation step. Validation step is used when you want to tune your hyperparameters. What is hyperparameters? Have you done deep learning before? Not yet. Any machine learning? Linear regression? Huh?
I am a user.
User. No, I mean, have you, okay, what are the models that you know? Maybe just throw a name.
YOLO is that
Huh?
machine learning? YOLO number 8.
Yeah, YOLO number 8 is, I think, classification or detection?
Detection.
Detection. Okay, YOLO number 8 is detection using deep learning. The backbone is deep learning. If you train YOLO number 8, that was your training step. But the thing is, with this YOLO number 8, which is similar to other deep learning, you have to adjust learning rate, number of epochs, or even the size of your data. These are hyperparameters. They are the parameters that are separated from the parameters of the deep learning itself. And when I say parameters of deep learning itself, I'm referring to the weights in the convolutional layers that you have to learn. So, or maybe let me give you this example. If you have a linear model, linear regression, where your fx is equal to x transpose beta, and beta is your parameters. Let's say you may be written this as x1 beta 1 plus x2 beta 2. Let's say you have only this model and you want to regress this value into a y hat. So given an input x, you want it to shape something for you as y hat, and you have a reference for y hat as y. Let's say this is just a single set of your data. Then, okay, in your training step, what you would want to do is that you want to train for your beta. Then your beta will be like a parameter set. Or in the other words, your parameter set will contain of beta 1, beta 2. It depends on how complicated your model is going to be. Okay? And yes, actually betas, this parameter set should include something like your function that was linear function, your fx. But I would use it as f dot like this, because it's actually like to denote that your function of being linear function is another factor for you to consider. Because you can do something like x1 beta 1 plus x2 beta 2 squared. If it's squared like this, of course, f will be different. Will be something that else, let's say gx. That's your, let's say, polynomial function. But whatever function you choose, that is your parameters. Thing is, when you try to train your model, and usually training will involve, let's say, setting up an optimization problem for learning it. Let's say you may be learning beta 1 and beta 2 by subtracting y, by learning that this value, which is y hat, should be matching with your observation y. It could be something like this, square, right? Least square error. But the thing is, if you do it this way, that means that you have one observation and you're trying to optimize for two unknowns, which is not good. That means you need like a whole set of training to help you learn these two parameters. At least you need two observations for this to give you like a unique solution for your beta, right? So maybe let me just use like a normal linear model. This may be easier to see. So this means that maybe you have to have like a J sample. I put it as a superscript for X and subscript for Y, and some J equal from 1 to M. This means that you need M samples for training. And at your training step, you are learning for beta 1 and beta 2. Okay, let's say the learned one is called beta 1, beta 2 hat. Okay, after you have beta 1, beta 2, in your testing step, what you would do is that you will infer y hat as a function of x and the beta 1, beta 2, and this one is like given beta 1, beta 2. Or maybe let's just call it x1 beta 1 hat plus x2 beta 2 hat will be equal to your forecasting value. But keep in mind that whatever data that you use when you train, you should not use it when you test. Because otherwise, whatever you get from here will already be the minimized version of that, right? Because you are setting it up as an argument min. Sorry, I should use like a min. Maybe min is better. Arg min. Sorry, I forget the min. Yes. So you need, first step, training data for solving this equation. And then testing data for testing this performance when you deploy. Why then you need the validation step? If you look at this, you have beta 1 and beta 2. It's only 2 parameters. What if you add beta 4, beta 5, or even beta 0, that is like a DC component, let's say. What if you add just beta 0 here, and your quality is better? How will you know whether or not you need this beta 0, or you just need beta 1, beta 2, or you need up until beta 4? To find how many model parameters that you need, you may need additional step that is called validation step. And of course, you need like a validating data. So this validating data will be used for finding the hyperparameters, and in this case, it will be the number of parameters. But of course, if you need more number of parameters, let's say you have beta 3, very likely you will also need your inputs, not just x1 or x2, but you also need x3, x4. And for that means your input sample will have to be of higher dimension, or sometimes we call it features. Let's say in his class that in his work he's done model detection with YOLO. His input is an image. A picture of size, let's say 256 times 256 itself is an input of feature size 256 square. Because every pixels in that can be used to multiply with your data here. That is the feature dimension. So yes, maybe let's recap. You can have input as many feature dimensions if your data allow, I would say. But then it may allow you to use more number of parameters. But to know how many number of parameters are going to be good enough for your model, you need a step that is called a validation step to find that number. And as you can see, this number of parameters very likely has nothing to do with how you would get the beta hat. So it's separated. It's not training, but it's more like another step where you're validating whether or not your assumption is correct. But then at the end, when you make decision that, okay, maybe just beta 1 and beta 2 is good enough, I don't need up until beta 10, then you test your model performance on the testing step. So that's like the whole entire reason why you need 3 steps. Is that any question? Okay, so can I have a break for like 10 minutes?